Hello everyone. So, for today's class, we'll start with the mathematics, physics, and imaging for magnetic resonance imaging, that is MRI. So, before we get into the instrumentation part of our MRI systems, we should understand the basic concepts which are required to understand how MRI machine works. So, we'll just go through a quick recap of the different terminologies and the different principles that are the basic concepts we need to understand to study about MRI. So, first, the contents, the trigonometric functions we'll be seeing the formulas, phase difference, we'll see what is phase difference, we'll study about vectors, periodicity, phase diagrams, sampling, Fourier analysis, and exponential decay. So, all these things are like the mathematics that are needed to understand the magnetic resonance imaging. So, first, magnetic resonance imaging is like the flexible imaging modalities which is still in use, like ever since nuclear magnetic resonance was discovered for medicinal applications. This is one of the best imaging modalities that is existing. So, magnetic resonance imaging, the main thing is the pulse sequences. So, whatever the pulse signal which we get from that imaging, that gives us the clear idea of the tissues which we are actually observing. So, MRI is quite a useful imaging modality which is in clinical use. So, a tissue can be made to give a signal which is higher or lower than another tissue, or it can give no signal at all. So, basically, when you image your head using MRI, like the skull can be ignored. So, when you set the pulse accordingly, you can remove the skull and view only the brain alone. So, the skull doesn't give any signal, something like that. So, we can perform different kind of imaging using MRI system. So, we would have studied about X-rays in your first unit, right? So, X-ray is an electromagnetic radiation with higher frequency. So, electromagnetic radiation is involved in MRI also, but in a different way. So, the radiation has a much lower frequency when compared to X-rays. So, it is not attenuated by the tissue and then detected. So, radiation is like one of the main components of nuclear magnetic resonance. So, whatever the radiation which is happening, it is an interaction between the nuclei and the strong magnetic field. So, basically, we have a big magnet which is surrounding the body, and whenever this magnetic field is interacting with the atoms inside our body, we will be able to see the tissues inside our body. So, basically we are looking for hydrogen nuclei, which is most abundant inside our human body because our body is made up of water molecules, right? So, in that water molecule we have hydrogen protons. So, this is what is the interaction between the atoms inside the body and the magnetic field. So, we will be able to get the information about the tissue by measuring the signals that are emitted by the hydrogen nuclei. So, we'll see some basic principles and concepts before getting into the detail of nuclear magnetic resonance. So, why we need to study all these things? Only if we know the basics enough, you will be able to understand the MR reconstruction and how the signals are detected, all those things. So, we'll start with the mathematics for MRI. First, the trigonometric functions. So, you have studied this in your engineering mathematics and before that also. So, you have a right angle triangle, you have a hypotenuse adjacent side and opposite side, and there is an angle theta. So, you have tan theta, sin theta, and cos theta. You have your formulas like tan theta is equal to opposite by adjacent side, sin theta equal to opposite by hypotenuse, and cos theta equal to adjacent side by hypotenuse. So, for each we can measure the angle theta, which is given by these formulas, and then this is like the standard formula which everybody will remember, right? Sin square theta plus cos square theta is equal to 1, and these are some of the commonly used angles in your trigonometric functions, like in terms of degrees and in terms of radians. So, in degrees you have 0, 90, 180, 270 and 360, and in terms of radians you will write it as 0, pi by 2, pi, 3 pi by 2 and 2 pi. So, these are just the basic trigonometric things you should remember. And the next term which is very important in your MRI studies is the phase difference. So what is phase basically? Basically phase is something like whenever you have a signal and then you find there is a angle change in that signal, then that is called a phase. So if you look at this figure, you have a sine theta and a cos theta. So basically the sine theta is starting at 0 and then the wave is propagating, and the cos theta has started much before 0, right? So there is a phase difference of 90 degrees. This is what we mean by phase difference. So you can see this figure has only one cycle, and then there is a difference of pi by 2. This pi by 2 is called your phase shift or phase difference. So although the two functions are very similar, like it has one upper peak and a lower peak, but then there is a phase difference of pi by 2. So this is what we mean by phase difference. Next thing which is very important in your MRI studies is vectors. So what is a vector? A vector is a quantity that has both amplitude and a direction. So it can be plotted using rectangular coordinate or a polar coordinate. So in terms of polar coordinate, you will have an amplitude and an angle. So if you look at this figure, it has an x-axis and a y-axis. So the amplitude is A, which is indicated by an arrow, and there is an angle which is alpha, and you have x and y coordinates. So the amplitude is given by A equal to square root of x square plus y square, and the angle alpha is given by tan inverse of y by x. So this is how you study the vector direction, right? Next one is resolving vectors. So whenever we study about vectors, the coordinate and the direction is very important, right? So a vector can be broken down into its component vector, which is at right angles to each other. These right angle components are called orthogonal components. So when you break down a vector into its orthogonal components, this process is called resolving a vector. So so far we have seen about vector in 2 dimension, right? So when you study the vector in 3 dimension, this is actually applicable in your MRI system. So in MRI, we will be studying vectors in 3 dimensions. So in 3 dimension, you can resolve the vector as one in z direction, which is in a longitudinal direction, and another one in xy direction, that is the transverse direction. Or you can again resolve it into x and y components. Like I'll explain this in the upcoming figure. So this xy plane is called real and imaginary component, which is nothing but your in phase and in quadrature components. So this in phase and in quadrature is your terminology which is used in your MR signal analysis. So if you look at this figure, you can see the left figure, which is your figure A. You can see a xy component and an z component. So you are actually dividing the 3D vector into two components. That is, one is in xy is between x and y, and another component is z. So you have a z component and a xy component. If you look at figure B, you have z component, y component and x component. So actually you have divided the xy component into x and y. So this is how you can study the 3-dimensional vectors. So this studying 3-dimensional vectors is a very important principle in your MR imaging. Okay. Next thing is periodicity. So far we have seen about trigonometry and vector. Next one is periodicity. So periodic signals are made up of repeated waveforms, right? A cycle is a part of the waveform which is repeated. So that cycle which is repeating is what is called as frequency. So the length of the cycle is wavelength, and the time period is called and the time limit is called a period. So linear frequency is cycles per second. It is measured in hertz. And then there is an angular frequency which is measured in radians per second. So you have two different frequency, linear frequency and angular frequency. So now the linear and angular frequency can be related as omega equal to 2 pi f. This formula also you would have studied in your signals, DSP and all those things. So this is about the periodicity. Next one is phase diagram. So when you plot the periodic function in terms of an angular coordinate system, then it is called a phase diagram. So why we need to study this? We need to understand the phase difference between the different functions, right? So the phase diagram has an arrow which is called a phasor, which rotates around a fixed point, that is between 0 to 2 pi. Usually in phasor diagram we rotate this phasor in an anti-clockwise direction. So this is how you draw the phasor diagram. You can see it starts from 0 and it goes up to 2 pi. You can see it is rotating in the anti-clockwise direction. So 0, pi by 4, pi by 2, 3 pi by 4 and pi, and it goes on. So at each point you can actually see the waveform. Like this is in a rotational phasor diagram, and the right side you can see a sinusoidal waveform. So this is what is a phase diagram. So as the left of the phasor is shown at various positions in the anti-clockwise direction through 2 pi radians. So this is what is a phase diagram. This is also important. Next thing is sampling. So what is sampling? Sampling is basically you are dividing a continuous time signal into a discrete time signal with some interval, right? So it follows the Shannon sampling theorem. What is sampling theorem? Any signal has to be sampled at twice the maximum frequency, right? So when you don't follow the sampling theorem, you will get the effect of aliasing. What is aliasing? The signal will be overlapped, and then you will have information loss. So that is what happens in aliasing, right? So that is otherwise called as undersampling. So when you actually don't follow the sampling theorem, the signal will be undersampled. So you will lose the most of the information content. So you can see here, so this figure is a classic example of aliasing. So the original figure is in the sinusoidal wave, which is in the continuous line, and if you look at the dotted line, that is what the aliasing effect, that is when you sample the sinusoidal waveform with a frequency less than twice the maximum frequency, you will get a waveform like this. Like the original signal has multiple upper and lower peaks, but when you look at the reconstructed waveform, you can see only one upper peak and lower peak, so you have lost most of the information. So that is why it is very important to follow the sampling theorem while reconstructing the signal. So why this is important? In MR also we'll get the signals, right? So the signals has to be reconstructed properly to get the information about the tissues which we are imaging. Say, like for example, if you are imaging a brain tumor and if you are not reconstructing the signal properly, then you will not be able to find the brain tumor inside the brain, right? So this is very important principle in MRI imaging. Next thing is Fourier analysis. So whenever we talk about signals, we definitely go for Fourier analysis. So Fourier analysis is you are converting the generic definition is you are looking at the signal in terms of frequency rather than the time domain, right? So we'll convert the signal from time domain to frequency domain and then do some analysis in the frequency domain. So this is for extracting the information about the composition of a signal. So in MRI we have to remember the important points in Fourier analysis, that is any signal can be expressed as a series of sine and cosine terms, and then when you plot the graph in terms of amplitude and frequency, then it is called a spectrum. So the spectrum is a visual indication of the amount of frequency, and the higher frequency terms are essential to get the fine details of a signal. And Fourier transformation is performed in MRI signals, and FFT is one computational method which is used for Fourier transformation. So this is about the Fourier analysis. Next one is exponential decay. So you would have studied about different types of signals, right? So an exponential signal is you will have e power minus 80, right? So that is what the classic formula is. So it's a mathematical function which has very important properties and interesting properties. So you can either express it as a naught e power minus bx or a naught exponential minus bx. So if you look at the figure here, you can see there is a x and then there is a in y axis. So x is your function of time and a is your amplitude. So you can see it's an exponential decaying function. So in the figure, the change in x needed to reduce a from a naught to a naught by 2 is indicated. So the amplitude, when you have to reduce the amplitude, you can look at the particular time. So I have indicated it as a red line here. So the a naught by 2 and the corresponding x value is indicated by this line. So similarly for different amplitude values we can look at the particular x values. So any factor we can take to minimize the decaying exponential. So this is how an exponential function is expressed. In exponential function you have something called a time constant. So the time constant is usually written as exponential minus t by tau. So that tau is your time constant. So in exponential decay, which is like a thing which is very common in your MRI system, so this time constant is defined as the time taken to get to a point on the curve where the value is e power minus 1. So when t is equal to tau, that is where your time constant is defined. So e has a value of 2.7, and when t is equal to tau, that point is usually 0.37 of the original signal. So if you look at the figure, you have your x-axis as time per second and y-axis as exponential of minus t by tau, and the line, you can see there is an exponential decaying function and there is a straight line. So this straight line is your 0.37. So at this point your time constant will be equal to your original signal time, that is t is equal to tau. So here you can see the exponential signal with different tau values. So tau equal to 1, tau equal to 2, 3, 4 and 5. So when you are varying the tau value, you can see how the signal is changing. So this is an exponential decay function with different values of tau. Similarly, exponentially rising function. Here also we are changing the time constant, and exponentially rising function is given by 1 minus exponential of minus t by tau. So here we are just looking at the different tau values, that is your time constant values. Next thing is exponential envelope. So if a periodic function is multiplied by exponential decay, the periodic function maintains its frequency, it maintains its frequency, but its amplitude is modulated by an envelope like the decay curve. So this is how the signal looks. When you have a sine signal multiplied by an exponential function, your sine signal will maintain its frequency. This is the cosine signal. So the cosine signal will maintain its frequency, but the amplitude will keep on decreasing as per the exponential decay. So this is an exponential envelope. If you look at the outer dotted line, that is the exponential envelope. So all these things are referred from this book. So this is just to understand about the basics about your MRI systems. So in the next lecture we will look at the physics of MRI.